Welcome! In this session, we'll dive into problem number 878, titled Nth Magical Number. This is a fascinating challenge that combines number theory and efficient algorithms to compute the nth magical number based on given constraints. Get ready to explore various approaches and refine your problem-solving skills. In this problem, we are tasked with finding the nth magical number. A number is defined as magical if it is divisible by either A or B. Our goal is to determine the nth smallest magical number, but instead of returning the raw number, we will return it modulo 10 to the power of 9 plus 7 to ensure we handle very large values efficiently. The input consists of three parameters, n, a, and b. Here, n is the position of the magical number we need to find, and it can go up to 10 to the power of 9. A and b are the divisors that define the magical numbers, and both of these values lie between 2 and 4 * 10 to the power of 4. The output will simply be the nth magical number after applying the modulo operation. Let's consider an example. When n equals 1, a equals 2, and b equals 3, the output is 2 because the smallest magical number divisible by either 2 or 3 is 2 itself. To better understand, let's look further into the examples. For the input n equals 4, a equals 2, and b equals 3, the output is 6. Why? Because the sequence of magical numbers divisible by 2 or 3 is 2, 3, 4, 6, 8. Here, the fourth magical number in this sequence is 6. Now consider another case. If n equals 5, a equals 2, and b equals 4, we need to identify the fifth magical number. The sequence of numbers divisible by 2 or 4 begins with 2, 4, 6, 8, 10. This means the fifth magical number in this sequence is 10. These examples highlight how the divisors at NB determine the sequence and how to identify the nth magical number. With these examples in mind, let's also examine the constraints and edge cases for this problem. First, the value of n can be as large as 10 to the power of 9, which makes it impractical to generate all magical numbers up to the nth one. This means the solution must be optimized to efficiently calculate the answer. Next, if a and b are equal, the sequence of magical numbers simplifies to multiples of a, making the nth magical number simply an asterisk a. Additionally, if a and b are coprime, meaning they have no common divisors other than 1, their least common multiple, or LCM, will be a asterisk b. Finally, if a and b share common divisors, their LCM must be calculated to accurately determine how the sequences overlap. These observations are key to handling different scenarios effectively. To solve this problem optimally, it's crucial to leverage binary search strategies alongside mathematical concepts like the relationship between divisors and the least common multiple. Binary search allows us to efficiently pinpoint the nth magical number in the sequence without explicitly generating all the numbers, which is vital given the constraints of this problem. By combining these techniques, we can develop a solution that is both efficient and accurate, even for very large input sizes. Let's now explore how to apply these ideas in the actual implementation. To tackle the nth magical number problem, the most straightforward approach we can consider is brute force. Here, the intuition is simple: iterate over all positive integers and check if each number is divisible by either a or b. If a number meets this condition, we increment a counter to keep track of how many such magical numbers we've found. Once the counter reaches n, we stop the process and return the nth magical number modulo 10 to the power of 9 plus 7. The steps are clear: start at 1, check divisibility, count qualifying numbers, and stop when the desired count is reached. However, the major drawback here is efficiency. The time complexity is O, n asterisk max, a, b, as we may end up checking a lot of numbers that aren't divisible by a or b. This makes the brute force method impractical for large values of n, a, or b. The inefficiency of the brute force approach brings us to a more optimized solution using binary search. The key insight here is that instead of iterating over all integers, we can directly calculate how many magical numbers are less than or equal to a given number x. This is done using the formula, count x equals x // a plus x // b x // LCM, a, b. The formula works by summing up the counts of multiples of a and b, then subtracting the double-counted numbers that are divisible by both, which are determined by their least common multiple, or LCM, a, b. This mathematical observation is crucial because it reveals that magical numbers are distributed in a periodic pattern based on A and B. By leveraging this periodicity, we can perform a binary search over the range 1 n asterisk min a b to efficiently locate the nth magical number, significantly reducing the computational workload compared to brute force. Now, let's break down the steps of the binary search approach. First, we compute the least common multiple of a and b, as this is central to the formula for counting magical numbers. Next, we define our search range as 1 n asterisk min a b, since this upper bound ensures we'll capture at least n magical numbers. During the binary search, we calculate the midpoint of the current range and use the count mid formula to determine how many magical numbers exist up to that point. If the count is less than n, it means the nth magical number lies to the right, so we shift the lower bound upwards. Otherwise, we adjust the upper bound downwards. Once the binary search converges to a single value, we return low %, 10 to the power of 9 plus 7, as the result. This approach is highly efficient, with a time complexity of O log n asterisk min a b asterisk log max a b due to the binary search and the calculation of LCM. It's also space efficient, requiring only O1 extra space. While the method is mathematically driven and requires a deeper understanding of concepts like LCM and binary search, it's extremely effective for large inputs, making it a powerful strategy. Given the inefficiencies of brute force and the strengths of binary search, the optimized binary search approach is the clear choice for solving this problem. Brute force, while easy to implement, is impractical for large values of n, a, or b due to its high time complexity. On the other hand, binary search minimizes unnecessary computations by leveraging the periodicity of magical numbers, which arises from the relationship between a, b, and their LCM. This allows us to efficiently narrow down the range and directly compute the count of magical numbers at any given point. The trade-off is that binary search requires a stronger grasp of mathematical concepts and more careful implementation, but the significant performance gains justify this added complexity. Ultimately, binary search strikes the right balance between efficiency and implementation complexity, making it the most suitable solution for finding the nth magical number. To solve the problem of finding the nth magical number, we start by understanding what makes a number magical. A number is magical if it is divisible by either a or b. Our task is to identify the nth smallest such number given the integers n, a, and b. Let's first look at a simple brute force approach. We initialize a counter to track the number of magical numbers we've found. Then, we iterate through integers starting from 1 and check whether each number is divisible by a or b using the modulus operator. If it is, we increment the counter. Once the counter reaches n, the current number is the nth magical number, and we return it. While this approach is simple to understand, it's inefficient for large inputs because we may need to check many numbers. To address this inefficiency, we turn to a more optimized solution, binary search. This method significantly reduces the number of calculations required to find the nth magical number. The optimized binary search approach begins by defining a search space. The nth magical number must fall within the range from 1 to n asterisk min a, b. This upper bound is based on the assumption that, in the worst case, every magical number could be divisible by the smaller of a and b. Next, we initialize low and high to this range and repeatedly narrow it down. In each iteration, we calculate the midpoint, mid, and determine how many magical numbers are less than or equal to mid. To do this efficiently, we use the formula count equals mid // a plus mid // b mid // LCM a, b. This formula combines the counts of numbers divisible by a and b, while subtracting those divisible by their least common multiple to avoid double counting. Based on the count, we adjust the search range. If the count is greater than or equal to n, the nth magical number must be on the lower side, so we set high equals mid. Otherwise, we set low equals mid plus 1. When the loop ends, low will point to the nth magical number, which we return as the result. To deepen our understanding, we can explore some key insights about the algorithm. First, when counting divisors, a number is divisible by a if the remainder of x% a is 0, and similarly for b. However, numbers divisible by both a and b are double counted, so we subtract the count of numbers divisible by their least common multiple. This ensures our counts are accurate. Second, binary search is highly efficient because it narrows the search range logarithmically. This makes it possible to handle even very large values of n, such as up to 10 to the power of 9, without iterating through all numbers. Finally, calculating the least common multiple plays a critical role in avoiding double counting. The formula for the LCM is *b/GCD a b, where the greatest common divisor is used to ensure the calculation is both efficient and avoids overflow when a and b are large. This algorithm relies on minimal data structures, which helps keep the implementation simple. We only use variables to store the bounds of the binary search, low and high, and a counter for calculating the number of magical numbers. All operations are arithmetic, so no extra memory is needed beyond these variables. The mathematical functions for GCD and LCM are essential for accurate calculations, particularly for handling double counting and ensuring efficiency. In terms of complexity, the time complexity is determined by the binary search, which performs O, log, and *min, a, b steps. Each step involves arithmetic calculations to compute the count of magical numbers, which is done in constant time, leading to an overall time complexity of O, log, and *min, a, b. The space complexity is constant, O, 1, as we use no additional memory apart from a few variables. This makes the algorithm not only fast but also highly memory efficient. This code solves the problem of finding the nth magical number, where a number is considered magical if it is divisible by either O or B. First, it defines the helper functions GCD and LCM to compute the greatest common divisor and least common multiple of A and B, respectively. These are critical to efficiently handle numbers divisible by both A and B. Next, the code sets up binary search over the range of possible magical numbers, which spans from 1 to n*min, a, b. The binary search works by calculating the midpoint of the range and counting how many magical numbers are less than or equal to mid. The count is computed using integer division, mid//a plus mid//b, mid//LCM_b. The subtraction accounts for double counting numbers divisible by both A and B. If the count is less than n, it means the nth magical number is larger than mid, so we adjust the lower bound of the binary search range. Otherwise, we adjust the upper bound. The search continues until the range narrows to a single value, which is the nth magical number. Finally, the result is returned modulo 10 to the power of 9 plus 7, as required by the problem constraints. This approach is efficient, leveraging binary search and mathematical properties to avoid directly generating all magical numbers, which would be computationally expensive for large inputs. Here, we begin by defining the solution class and implementing some helper methods to solve the problem. First, we have a GCD method, which calculates the greatest common divisor of two numbers using the Euclidean algorithm. This is crucial for finding the least common multiple, or LCM, which we calculate in the LCM method. The formula for the LCM is the product of the two numbers divided by their GCD. These helper methods simplify the calculations needed later in our solution. Now, looking at the nth magical number method, we start by defining the modulo constant mod as 1,000,007 since we need to return the result modulo this value. Then, we compute the LCM of A and B, which allows us to account for numbers that are divisible by both A and B. Next, we initialize a binary search range with low set to 1 and high set to the product of n and the smaller of A and B. This range represents the possible values for the nth magical number. The binary search loop begins, where we calculate the midpoint, mid, and determine how many magical numbers exist up to that point. The count is obtained by summing the integers divisible by A and B, and subtracting those divisible by their LCM to avoid double counting. If the count is less than n, it means we need to search in the upper half, so we adjust low to mid plus 1. If the count is greater than or equal to n, we narrow the search space by setting high to mid. This process continues until low equals high, at which point the binary search terminates. The value of low now represents the nth magical number. Lastly, we return the result as low modulo mod, ensuring that the output adheres to the problem's constraints. By leveraging the efficiency of binary search and modular arithmetic, this implementation achieves optimal performance for finding the nth magical number. In this problem, we aim to find the nth magical number, or a magical number is divisible by either A or B. To solve this efficiently, we use a binary search approach. Let's consider the example where n equals 5, A equals 2, and B equals 3. First, we calculate the least common multiple, or LCM, of A and B. This is done using the greatest common divisor, or GCD. The GCD of 2 and 3 is 1, so the LCM is calculated as 2 times 3 divided by 1, which equals 6. With the LCM in hand, we set up binary search bounds. The lower bound starts at 1, and the upper bound is computed as n multiplied by the smaller of A and B, which in this case is 5 times 2, giving us an upper bound of 10. Now, we perform the binary search to find the nth magical number. In the first iteration, we calculate the midpoint as the average of the current low and high bounds, which is 1 plus 10, divided by 2, resulting in 5. Next, we count how many magical numbers are less than or equal to 5. This is done using the formula, mid divided by A, plus mid divided by B, minus mid divided by the LCM. Substituting the values, we get 5 divided by 2, plus 5 divided by 3, minus 5 divided by 6, which equals 2 plus 1 minus 0, giving a count of 3. Since this count is less than n, we adjust the low bound to mid plus 1, which is 6. In the second iteration, the midpoint becomes 6 plus 10, divided by 2, giving 8. Counting the magical numbers up to 8, we get 8 divided by 2, plus 8 divided by 3, minus 8 divided by 6, which equals 4 plus 2 minus 1, for a total of 5. As this matches n, we update the high bound of 8. In the third iteration, the midpoint is 6 plus 8, divided by 2, resulting in 7. Counting up to 7, we find 7 divided by 2, plus 7 divided by 3, minus 7 divided by 6, which equals 3 plus 2 minus 1, totaling 4. Since this is less than n, we set the low bound to 8. When the low and high bounds converge at 8, the search ends. The result, modulo 10 to the power of 9 plus 7, is 8. For the next example, we consider n equals 4, A equals 4, and B equals 6. First, we calculate the LCM. The GCD of 4 and 6 is 2, so the LCM is 4 times 6, divided by 2, which equals 12. With the LCM computed, we set up the binary search bounds. The lower bound starts at 1, and the upper bound is calculated as n times the smaller of A and B. In this case, it's 4 times 4, resulting in an upper bound of 16. Next, we apply binary search to determine the nth magical number. In the first iteration, the midpoint is calculated as 1 plus 16, divided by 2, which equals 8. Counting the magical numbers up to 8, we compute 8 divided by 4, plus 8 divided by 6, minus 8 divided by 12, yielding 2 plus 1 minus 0, for a total of 3. Since this count is less than n, we adjust the low bound to mid plus 1, which is 9. In the second iteration, the midpoint becomes 9 plus 16, divided by 2, giving 12. Counting up to 12, we find 12 divided by 4, plus 12 divided by 6, minus 12 divided by 12, which equals 3 plus 2 minus 1, for a total of 4. As this matches n, we update the high bound to 12. In the third iteration, the midpoint is 9 plus 12, divided by 2, resulting in 10. Counting up to 10, we calculate 10 divided by 4, plus 10 divided by 6, minus 10 divided by 12, which equals 2 plus 1 minus 0, totaling 3. Since the count is less than n, we set the low bound to 11. In the fourth iteration, the midpoint becomes 11 plus 12, divided by 2, which equals 11. Counting up to 11, we compute 11 divided by 4, plus 11 divided by 6, minus 11 divided by 12, yielding 2 plus 1 minus 0, for a total of 3. Again, the count is less than n, so we update the low bound to 12. When the low and high bounds converge at 12, the search ends. The result, modulo 10 to the power of 9 plus 7, is 12. Thus, the final output for this example is 12. Now, let's examine the next case where n equals 3, A equals 8, and B equals 9. First, we calculate the LCM. The GCD of 8 and 9 is 1, so the LCM is 8 times 9, divided by 1, which equals 72. With the LCM determined, we set the binary search bounds. The lower bound starts at 1, and the upper bound is computed as n times the smaller of A and B. Here, it's 3 times 8, resulting in an upper bound of 24. Using binary search, we proceed to find the nth magical number. In the first iteration, the midpoint is 1 plus 24, divided by 2, which equals 12. Counting the magical numbers up to 12, we compute 12 divided by 8, plus 12 divided by 9, minus 12 divided by 72, yielding 1 plus 1 minus 0, for a total of 2. Since this count is less than n, we adjust the low bound to mid plus 1, which is 13. In the second iteration, the midpoint becomes 13 plus 24, divided by 2, giving 18. Counting up to 18, we calculate 18 divided by 8, plus 18 divided by 9, minus 18 divided by 72, which equals 2 plus 2 minus 0, for a total of 4. As this count is greater than n, we update the high bound to 18. In the third iteration, the midpoint is 13 plus 18, divided by 2, resulting in 15. Counting up to 15, we find 15 divided by 8, plus 15 divided by 9, minus 15 divided by 72, which equals 1 plus 1 minus 0, totaling 2. Since the count is less than n, we set the low bound to 16. In the fourth iteration, the midpoint becomes 16 plus 18, divided by 2, which equals 17. Counting up to 17, we calculate 17 divided by 8, plus 17 divided by 9, minus 17 divided by 72, yielding 2 plus 1 minus 0, for a total of 3. As this matches n, we update the high bound to 17. When the low and high bounds converge at 17, the search ends. The result, modulo 10 to the power of 9 plus 7, is 17. Thus, the final output for this example is 17. With the binary search approach, we've seen how to efficiently compute the nth magical number for different inputs by leveraging the properties of divisors, the LCM, and count calculations. This concludes the solution walkthrough for the problem. In this problem, we calculate the nth magical number using binary search combined with mathematical operations. To understand the time complexity, let's first break down the components. The first operation is the computation of the greatest common divisor, or GCD, using the Euclidean algorithm. This method is highly efficient, with a time complexity of O log min a b. Since the least common multiple, or LCM, is derived from the formula LCM a b equals *b / GCD a b, its computation is also dominated by the GCD operation, making its complexity O log min a b. Next, binary search is performed over the range from 1 to n multiplied by the smaller of the two divisors, min a b. Each iteration of binary search reduces the range by half, and the total number of iterations is proportional to the logarithm of the search range. Since the range depends on n and min a b, the binary search requires O log n * min a b iterations. These two steps provide the foundation for our time complexity analysis. Now, let's analyze the count calculation step. During each binary search iteration, we need to compute how many magical numbers are less than or equal to the current midpoint. This is achieved using the formula count equals mid / a plus mid / b mid / LCM _b. Each division operation within this formula is constant time, meaning the entire count calculation is performed in O1 time. Since binary search performs O log n * min a b iterations, and each iteration requires O1 time for the count calculation, the total time complexity of the binary search step is O log n * min a b. Finally, combining the time complexities of the GCD, LCM, and binary search steps, the overall time complexity of the algorithm is dominated by binary search. This gives us a total complexity of O log min a b plus log n * min a b. However, since log min a b is constant relative to n, the final complexity simplifies to O log n * min a b. Now let's shift our focus to the space complexity of the algorithm. The algorithm is highly efficient in terms of space usage, as it only requires a constant amount of extra memory. First, we store a few scalar variables such as mod, LCM _b, low, high, mid, and count. Since these are simple variables, they only take up O1 space. The GCD function, which is used during the computation of the LCM, is implemented iteratively rather than recursively, so it does not add any extra space for a recursive call stack. Moreover, the algorithm does not utilize any additional data structures such as arrays, lists, or hash maps. As a result, the total space complexity is 1, making this solution very memory efficient. When comparing this solution to a brute force approach, the difference in efficiency becomes clear. A naive solution would involve iterating through all numbers to determine the nth magical number. In the worst case, this means testing divisibility for every number up to n times min a, b, resulting in a time complexity of n asterisk min a, b. This approach is highly inefficient when n or the divisors are large. In contrast, the binary search method drastically reduces the number of iterations to O log n asterisk min a, b. By avoiding unnecessary checks and leveraging mathematical insights, the binary search solution is significantly more efficient. Additionally, the algorithm's best, average, and worst-case scenarios all have the same time complexity of O log n asterisk min a, b, since the binary search structure remains consistent regardless of input values. This consistency makes the current solution not only faster but also more predictable in terms of performance. To conclude, let's solidify our understanding of the time complexity with a mathematical proof. The binary search algorithm exhibits logarithmic behavior because it reduces the search range by half during each iteration. The GCD and LCM calculations, while essential, are constant time relative to the binary search range, and the count formula is evaluated in constant time as well. Combining these factors, the overall time complexity is determined by the dominant term, which comes from the binary search iterations. This results in a final complexity of O log n asterisk min a, b. This proof highlights how the algorithm efficiently narrows down the nth magical number, making it optimal for this problem. When tackling the nth magical number problem, there are some common mistakes to watch out for. One of the most frequent pitfalls is ignoring edge cases, such as 0 or negative inputs. While many problems assume positive integers, failing to account for these edge cases can lead to runtime errors or incorrect results. For example, if the divisors in the problem are 0, you could run into division by 0 errors or undefined behavior. Always check constraints and handle such cases explicitly. Another mistake is using inefficient brute force methods. Iterating through all numbers up to a large limit without leveraging properties like divisors or multiples can result in timeouts, especially for larger inputs. Instead, consider using mathematical shortcuts like calculating the least common multiple, or LCM, to optimize your approach. Lastly, off-by-one errors and bounds are a frequent issue. For instance, when iterating to count multiples, confirm whether the bounds should be inclusive or exclusive. Misaligning these boundaries can easily lead to incorrect results, so pay close attention to how limits are defined in the problem description. Another common issue is duplicate calculations when handling overlapping conditions. For example, when counting numbers divisible by a or b, those divisible by both will be counted twice. To fix this, you need to subtract the count of numbers divisible by the LCM of a and b to avoid double counting. Misinterpreting problem requirements is another area where errors often occur. For instance, failing to distinguish between exactly divisible and at least divisible by 1 can lead to incorrect logic. Such misunderstandings can derail your entire solution. To address this, always clarify ambiguous wording, especially in an interview setting. Taking a moment to ensure you fully understand the requirements can save you significant time and effort. In an interview scenario, optimization is key, especially for problems involving divisibility or large ranges. While brute force may seem like a straightforward solution, it's rarely sufficient. Instead, demonstrate your ability to optimize using mathematical properties such as LCM, GCD, or modular arithmetic. Additionally, if you're considering multiple approaches, always explain the trade-offs. For instance, you might discuss how a brute force solution has a time complexity of O(n), while an optimized approach could achieve O log n by leveraging mathematical formulas. Clear communication is also essential. Thinking aloud as you derive formulas or identify patterns helps the interviewer follow your thought process. Finally, don't forget to address edge cases up front, such as handling very small or very large inputs, or divisors like 1 or the number itself. This not only shows your thoroughness but also boosts your chances of implementing a robust solution. The nth magical number problem has similarities with several other LeetCode problems. For example, LeetCode 263, ugly number, involves checking if a number is divisible only by 2, 3, and 5. LeetCode 264, ugly number 2, extends this by asking for the nth ugly number using dynamic programming. Similarly, LeetCode 1201, ugly number 3, focuses on finding the nth number divisible by A, B, or C. Another related problem is LeetCode 400, nth digit, which involves finding the nth digit in an infinite sequence of integers. These problems share overlapping concepts, such as divisibility and counting within constraints. To solve such problems efficiently, mathematical approaches often come in handy. For instance, you can use the union of sets formula to count numbers divisible by A or B. This involves calculating the multiples of A and B individually, then subtracting the overlap, which is the count of numbers divisible by their LCM. This approach is much faster, as it avoids unnecessary iterations, but it requires a solid understanding of concepts like LCM and modular arithmetic. For more advanced efficiency, binary search can be a powerful method. When finding the nth number divisible by A or B, you can use binary search to narrow down the range of possible values instead of iterating through all numbers. While this approach is more complex to implement, it offers logarithmic efficiency, making it well-suited for large constraints. Another viable approach is dynamic programming, which is particularly useful for problems with multiple constraints, like ugly number 2. By building up solutions incrementally, you can efficiently find the nth special number. However, dynamic programming often requires extra space and can be less intuitive compared to direct mathematical solutions. The choice of approach depends on the specific problem requirements and constraints, but understanding these trade-offs will help you decide which method to use in different scenarios. Great job! We've covered the nth magical number problem and explored how to efficiently solve it using binary search and modular arithmetic. Remember to practice applying these techniques to similar problems, as they are invaluable for interviews and competitive programming. Thanks for joining, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!